rest my legs a second. So there was a little bit of a glitch on the homework, which is now repaired. So if you didn't notice there was a glitch, then you should be totally unaffected. And if you did notice a glitch, then it's now fixed. So basically what happened was there were two identical assignments with different names on them. And for some reason, I must have switched one for the other back on Thursday. So what happened was that people logged in to finish their homework and realized that they didn't have any points when they had actually started. Anyway, totally taken care of. I have extended the due date for 2 days, so you have until Thursday night to finish. If you already finished, then you're done anyway, so that's good. And that's what we'll do. Any questions on that before we move on? Okay, so we got 2 more lectures before we will do a review next week. But we got 2 more lectures to finish up, so I'm going to continue through this chapter for what we call solid state physics, or the section that we focus on here is the semiconductors and applications for electronics. So I'm going to take up on this and review briefly where we left off. So last time we were talking, we considered the idea of a metal substance that could be considered as, if I took a cubic volume, as a particle constrained to an infinite square well. And the square well potential was infinite at the edge of the box because electrons cannot jump off. And from that, we use the density of states, which is the number of energy levels and quantum numbers within a given energy level, to determine how many states there were. And then the theory is that we consider these electrons as being free in the metal, free to move around, and we begin to fill them up from the lowest possible energy, which is very close to 0. And of course, this is kinetic energy. And because of the Pauli exclusion principle, that as the states get filled up for the particle in a box, so you remember the ground state had a half a sine wave for the wave function, and then the n equals 1 had a full sine wave, and n equals that was n equals 2. For n equals 3, we had 3 halves of a sine wave, and the energies continue to increase in proportion to n squared. So doing that, what we found was that the electrons continue to get stacked up in higher and higher energies, because according to the Pauli exclusion principle, they cannot all be at the ground state energy, which would be very, very close to E equals 0. So therefore, they are forced to be in energy states which are significantly get larger and larger. And if I add up to of order 10 to the 21st electrons, we calculated the number of electrons in a cubic centimeter last time of copper, free electrons, and the number is of the order between 10 to the 21st and 10 to the 23rd electrons, and I stack up those electrons one by one until I fill up all the energy levels, and when I get to the maximum, the last electron in the sample, I have what's called the Fermi energy, which is the maximum energy that the electron will have. And this was done at absolute 0 temperature. That is to say that the temperature scale, the temperature of the sample is absolute 0, which means that classically speaking, there would be no thermal energy that would be associated with the system. Now, normally the thermal energy is given by Boltzmann's factor. We've talked about that. K times the temperature, Boltzmann factor times the temperature gives a unit of energy, and that's thermal energy or kinetic energy per molecule or per electron or per particle in the gas. And so this is at absolute zero where everything is frozen out. We did a derivation, which is also in your reading material, to calculate the Fermi energy as an integration over the density of states. And the maximum energy, or EF, is this energy right here. And it is proportional to the density, the electron density in the material, where N is the number of electrons and V is the volume for those electrons. So that would be what we call the electron density. And we calculated that, and we came up with a number that the Fermi energy for copper was about 7 electron volts, which is what you see here. So for copper, the maximum energy is 7. The average energy is still very, is only 40% lower than that, or roughly 4.2 electron volts. So that even the average energy is very high, considering the fact that it's at absolute zero temperature. And it's all because of the Pauli exclusion principle, that we have to note we can't have all the electrons collapse down to their ground state energy. Okay. Then we talked about what happens when the temperature goes up above zero. And we said that the Boltzmann factor, which we had used before, for example, discussing the black body radiation, e to the EKT, E over KT, e to the minus E over KT, I'm sorry, gets replaced with this denominator right here. And this denominator is the function f of E. F of E is basically 1 over this exponential term right here, and that is the probability that an electron will be found in that state. And so this is a derivation that comes from thermal physics. Again, books did not have the ability to go through thermal physics, so we state it here without proof. But if I multiply the number of possible states, g of E, so that's this square root of E function that you can sort of see increasing as the square root here, then if the density of states times the probability that they're occupied there multiplied together will give us the number of the density of occupied states. And it only changes a little with temperature. So in other words, at absolute T equals 0, basically the population of the electrons in the different energies really don't look much different at T equals 0 as they do here at T equals 1200 degrees, which is right below the boiling point of copper. So the idea is that, but what you can see, and this is important later, is that as the temperature increases, some of the electrons at the highest energy level spill over into the electrons above the Fermi energy. So we do get some population above here. And keep in mind, this Fermi energy is the last energy of the last electron in the lattice. It's the highest energy that of all the electrons that can exist in the sample, which we did a derivation of. Okay. So this factor, which is the probability function, E to the E minus EF over KT plus 1, is a factor that's going to tell us what is the probability that an electron has a given energy, whether it's above the Fermi energy or below the Fermi energy. And you can see how it changes there. We worked through an example last time. This was the case of a copper metal. We determined the Fermi energy by its relation to the density of the material. So the density of copper was expressed in terms of electrons per cubic centimeter, assuming that we had 1 free electron for every atom. Then we take the number of atoms per cubic centimeter, and that tells us how many electrons per cubic centimeter there are. Right? So we did that last time, and that's how we came up with that number of 7 EV. The average energy is about 60% of that, so it's about 4.2. And then, of course, we do the speed calculation by converting EV to using 1/2 mv squared. And we did a brief calculation on that last time as well. Okay. Now, to get into the business, or moving towards a little bit towards the other types of materials, which are semiconductors and insulators, we are now going to introduce you to what's called the band theory of solids. And the basic idea of the band theory of solids is that unlike the hydrogen gas, where there are discrete energies that the electron can have in the atom, when you solve the Schrödinger equation for a solid material in a repetitive structured lattice, so these little black dots here represent the location of the atoms in the solid. And if it's a conductor, such as copper, then these will be the copper nuclei at these points right here. And there will be certain allowed energies that exist for electrons that are associated with these atoms. And what you can see here is that the blue shade area indicates that there are bands of energy that are available. And this comes purely from solving the Schrödinger equation, so it's not something that would be entirely intuitive. There's a little bit of discussion in your 12-page write-up online on the subject where they try to motivate the idea that when you solve the Schrödinger equation for solids, that you, instead of getting discrete energies, you get a lot of energies that are so closely spaced together that they essentially form a continuum. Okay? And we saw that with the electrons, just in the conductor, that those are discrete energy levels, but they're so close together that, that we talk about the density, how many states are there per electron volt, rather than specifying the exact electron volt. Because they're so close together that, and they reach up into the hundreds of billions, quadrillions, in terms of quantum numbers, that it doesn't make sense to characterize them any other way. So this idea is that electrons that are closer to the center of the nucleus will be bound at lower energies, and then you will have band structures at higher energies. And these are labeled bands by the traditional SPDF nomenclature, or the principal quantum number nomenclature, but they now form bands instead of discrete energies. It is a periodic lattice. So what you're seeing here is the red curve indicates the potential energy. Remember, this is the nucleus is a positively charged entity, right? It's got Z protons, therefore it has Z times the charge of electron, therefore it produces electric field. It produces electric field, therefore it has electric potential, and any other electron will experience the potential due to the positive charge. And that potential energy function for a Coulomb field, it goes like 1 over R, which typically would go, and where R equals 0 would be the location of the center of the atom. So the electric field obviously is very, very strong at the center or at the edge of the nucleus. But it's going to go like 1 over R as you move away from there, but it doesn't really continue and go all the way up to 0 like you have for the hydrogen atom, but it turns back down because there's another nucleus here, and another nucleus then creates the potential function where you get this periodic it looks like 1 over R on this side and 1 over R on this side, but it actually flattens out in between, because halfway in between the two positive charges, we expect that the force is 0, right? So the potential, the derivative potential, which is the slope, has to go to 0 halfway in between. If it's closer to one side or the other, then of course the force of attraction will push it in one way or the other. Now, also worth noting in this graph is that the highest band which is the upper blue band right here, is called the valence band. Valence, of course, meaning the energy levels accessible to the most energetic electrons in the atom. And the electrons with the highest energy are the least bound in the atom. And so there was a problem like this on your last exam, so you probably recognize this by now, that there is a minimum energy required to eject an electron from the surface of the metal, and of course that's a photoelectric effect, and that minimum energy is called the work function. It's the work function for that metal. In every metal, that value will be, I don't know why it's called function, because it's really a scalar value, and it doesn't really describe a function as something which is a function of a variable. But in any case, you can see it right here. The electric charge times the electric potential gives the total energy that's required to ionize an electron off the top of this conductive region. And notice in this case, well, we'll talk about this a little bit later, that there are regions between the bands which are called the gaps. And the gaps are what we call the forbidden energy region. So that's the region, those are the energies that the electrons cannot have in the material, right? And the blue area is the energies that the electron can have. Okay? So the bands are the allowed energies, the gaps are the unallowed energies. Okay? And this is purely something that comes out of the Schrödinger equation. There's not much way to describe it simpler or more directly than that, but this is basically the energy diagram, and we keep coming back to that because you have to understand the energy diagram. The best way to understand processes in atomic physics is by looking at the energy level diagrams, where you have potential, and the blue actually represents the total energy of the particle. The red represents potential energy, and we superimpose those so that you can see where they are. Notice that they are less than zero. The zero line up here is the energy that a particle will have to be completely free from the orbit, and if they are trapped, then they have to have what we call negative energy, which represents their binding energy to keep them within the crystal or within the solid. Okay, well that was a long-winded explanation, but I think it's important to try to understand these from the basic ideas. Another way we can go into more detail and look at these band structures for different types of atoms. The one that is given in the book is the one that is discussed, which is called sodium. And sodium, if you notice on the periodic table, it's located in the first group of the periodic table of elements, and this column right here has one valence electron, right? And we know that even if they were in the 1s, which of course these really are, these are all these atoms in the first table here, or for the most part, are have their outer electron in the S shell. It might be the 1s, the 2s, the 3s, or the 4s, but there's one electron there. And we represent that by this half-shaded area showing that there is one electron which is filling the 3s, but there is an unoccupied region up here which is also part of the 3s, because you can have two electrons in any given S state. You can have one with spin up and one with spin down. Right? And so if there's only one electron in the 3s, then there can be a second one, which of course is not shown here because the blue shaded means that these lower energies are filled up. Now notice that because we're dealing with a solid, we don't just have a single energy with the 1s, a single energy with the 2s, a single energy with the 2p, etc. But we get the band structure. And the band structure is basically a duplication of this that says if you're looking in terms of a solid or the energy levels within a solid, it's not the same as a single atom. Okay? The interaction of having all the atoms strung together give us this periodic potential function, which is not the same as the potential function of an electron in a sodium atom, or an electron in hydrogen, or any other. That only has 1 over r, right? It's 1 over r, it's infinite at r equals 0, and it's 0 at r equals infinity. This is a different potential function because it is the potential for a periodic lattice of atoms in a material. Right? That leads to the fact that that you don't just have a single energy, but you have a band of allowed energies. But the point is that because of the millions and billions of electrons available, the energy levels fill up, and in the case of sodium, which is an example shown here, it's an unfilled region. Now, the reason this is important is that this is a very important property of conductors. A conductive material is one in which there is an unfilled valence shell. Right? The outer shell is unfilled, and therefore, if I apply a voltage across the material, it is very easy for electrons, which they cannot simply push their way across from this 3s state to this. They can't occupy the same state as another electron, but they can bump up ever so slightly, and then drift across in what's called the unfilled region. So that is the feature of the electrons that we are seeking. It is an unfilled shell, and that unfilled shell allows electrons to propagate because they don't need very much energy to get to the next state, which in this case would be the spin up or the spin down state of the electron in the sodium atom. Whereas, so if this was spin up, for example, this one was spin down, the upper one would be spin up. That requires very, very little energy to be able to do that. Okay, so that's a conductor. So how does that differ from an insulator? Well, the insulator, so here's the conductor with the half-filled valence shell. So there are still a lot of unoccupied energy states slightly above the energy level of the filled, of the occupied states. And for reasons we just described, conductors can move into that relatively easily. And the reason they can do it relatively easily is that it doesn't require much thermal energy, because these energy differences are so small in the order of microvolts that the kinetic energy, which is 1/2 or 3/2 kT, is already like 0.03 electron volts. So the thermal energy is more than enough to be able to excite these electrons in the conductor. However, the general characteristic of an insulator is that it has a completely filled valence band, and it has a large energy gap into the band right above it, which is unfilled, and therefore the unfilled band is the one that you have to get to in order for electrons to move away from their atomic sites. And if this is a large energy difference, there's not enough thermal energy available, which in the case of room temperature, 3/2 kT is the thermal energy. That's approximately equal to 0.03 electron volts. And this energy gap is usually 4 or 5 electron volts. So there's just simply not enough thermal energy for these valence electrons to get up into the conduction band. Hence, those electrons cannot move. They are glued to the atomic site of their origin, and they will not flow or move across the material. Right? In that case, we have a condition that is the description of an insulator. Then we have, which is the final point that we're trying to get to in the last part of the course, is the third case, which is called a semiconductor. I guess there's a fourth one, which would be superconductivity, but we're not covering superconductors in this class. The case of the semiconductor, what we have is a case where the valence band is already filled, but there is a very small energy gap. Not terribly small, but a much smaller energy gap to get electrons thermally bumped up into the conduction band, and which is much easier than getting them pumped up into the conduction band, where I need a much larger energy jump in order to get those electrons up there. So, maybe I think we got an example to work out here in the coming. Let's stop right here. Are there any questions you want to ask about the general theory up to this point? How many people have seen this concepts before? Anybody? What? Not many. Okay. All right. Okay. Well, let's continue on and see if we can maybe try to make these things a little clearer. So you recall from the last slide, or the slide that we started with, that electron population at different energy levels in a conductor were given by this equation, which was the Fermi-Dirac population probability function times the density of states, and it looked something like this right here. So we can look at this denominator term more carefully, which is the function f of e. This is what I call the probability of it being in a given state, and we can use the Fermi-Dirac probability function to estimate how many electrons there are in the conduction band of a semiconductor, which has a certain number of atoms in a cubic centimeter, and assuming we're at room temperature and that the Fermi energy is at the top of the last filled subshell. So in other words, what we want to do is say is that suppose that we were looking at this case here, there's a completely filled band of electrons, and we want to know if it's what we call a semiconductor. And by the way, for orders of magnitude, this energy gap in a conductor is about 5 electron volts. For a semiconductor, the energy gap is about anywhere from 0.5 to 1 or 2, but sometimes even 3, but definitely smaller than you have for the conduction band. But what we can do, and this was worked out as an example in the in Gene Coley that you have available for your reading assignment, is to calculate what is the probability of finding an electron in the conduction band based on its thermal energy. So we look at a particular model to calculate that. We look at a particular model, and the model or the case that we consider is one in which we have an energy gap which is about half electron volt. The valence band is filled, and so the energy I need to be able to get into the conduction band has got to be a half, or in this case 0.55 eV higher than the Fermi energy. So the Fermi energy covers everything up to the top of the valence band. Okay? The energy levels are filled up, and in a semiconductor, the last valence band is completely filled. Right? But it doesn't have quite enough to get into the conduction band. But a few of them will get into the conduction band. Right? And the reason is because there is some finite temperature T greater than 0 that will allow this to occur. So a simple calculation says that the probability, f of e, the probability of making it, so this is the probability of electron occupying the conduction band, right, is given by 1 divided by e to the e minus ef over kt plus 1? Yeah, plus 1, right? And if I evaluate this for must be greater than or equal to the energy E must be greater than or equal to the Fermi energy plus the band gap energy, E gap. Okay. So I get that the minimum energy required is E minus EF is equal to the band gap energy. That is the energy that I need to be able to lift electrons into the conduction band. So this becomes E to the EG divided by KT plus 1. So that's E to the EG cap. So now EG in this case is only of order half of a electron volt. So I do E to the 0.55. Then I evaluate KT for room temperature, which this is 8.6 times 10 to the minus 5 times 300. So this is of order 0.025 eV. So I put in 0.025 here and plus 1, and I get that this probability then is approximately, if I evaluate this a little bit earlier today before class, is about 0.156. If I've done that correctly, right? Let me go ahead and verify it in my notes that that is close to what we expect. 1 second here. Nope, I'm sorry, my mistake. I was thinking of a different calculation. 1 second. 1 second. I'm going to go through this with the entire day. Oh, wait a second, 0.55. Something mistake. Let's be a little more careful. This is my mistake. Okay, yep. Let's look at this a little more carefully now. So this is actually E to the 0.55 times 40, which is E to the 20th, which is 10 to the 9th, roughly. So this probability F of E for a semiconductor is equal to approximately 10 to the minus 9. So this probability of electron making it to the next highest level is 1 in 10 to the 9. Now, usually conductors have 1 or 2 electrons that are free to move in the sample. That's a typical number for a conductor, 1 or 2 electrons. Only 1 in 10 to the 9 electrons, 1 in 10 to the 9 electrons make it to conduction band. Okay? If I have a conductor, if I'm dealing with a conductor, then every electron in the valence band is in the conduction band. Okay, so in particular, if in this particular example, if I have of order 10 to the 21 atoms in 0.01 cubic centimeters, which is something about 4 millimeters on the side of a very small piece of metal, then for a conductor, I will have 10 to the 21 conduction electrons. Right? If I do this for the semiconductor, then with only 1 in 10 to the 9th that make it to the conduction band, then the number that make it to there will be 10 to the 21 times 10 to the minus 9, which is equal to 10 to the, what is it, 12, 13, I can't do 12, 21 minus 9, 21, so 12, 12, right? And so 10 to the 12th electrons will make it to, will be in conduction band. Okay, that's still a number that is pretty reasonably large for a 4 millimeter piece of material, right? Not as big as 10 to the 21, but which we have for conductor, but it's still significant. Okay. Now, if I were to do the same calculation for the insulator, which is given in the middle row of the diagram, the one in the center, then that case, the energy gap is about equal to 5 electron volts, and F of E, which you can calculate for yourself, is of order 10 to the minus 42. Right? That's a very small probability because the energy gap is higher. So for an insulator, this number is equal to E to the 5 divided by 0.025 plus 1 inverse. Right? And this number is much, much smaller. Even if I multiply this by 10 to the 21 electrons, right, the probability of even one electron making it there is less than 10 to the minus 20. Okay? So insulators don't conduct. Right? That's the idea. Insulators don't conduct. And we can demonstrate it by using this probability function that was developed by Fermi and Dirac for the probability of an electron having a given energy as a function of the temperature. Okay. Any questions? Questions? Good time to ask questions. Okay. We got conductor, insulator, and semiconductor. Now, conductor, almost one electron on every atom is going to conduct. In a semiconductor, 1 in 10 to the 9 is going to conduct. An insulator, 1 in 10 to the 42 is going to conduct. Right? Yes?
Just repeat that one more time.
Yeah, for a conductor, every electron in the half-filled shell, unfilled shell, is going to conduct. There's of order 1 electron per atom, maybe 2, but let's say 1. So if I have 10 to 21 atoms, I have 10 to 21 conducting electrons. Okay. In this one, I have 10 to 21 times 10 to the minus 9, because the probability that it gets there is, no, I'm sorry, in this one, I've got 10 to 21 the valence electrons, but only 1 in 10 to 9 can make it up there. Right? So it conducts a little bit, hence the word semiconductor. And then for the insulator, the energy gap is so large that this exponential factor that's calculated from the Fermi becomes enormously small, and the probability of finding even 1 electron in the sample that can make it to the conduction band is extremely small. Right? Hence, it is an insulator. It will not conduct. You can apply a lot of voltage, no current's going to flow. Okay. Any questions? We good? Yeah? Make sense? Yeah? Okay. You said it makes sense, so I'm going to just take your word to go. Okay, example. I think, well, I'll mention just calculating the energy gap. Okay, so it is found that the conductivity of a certain semiconductor increases when light of a given wavelength or shorter impinges on it. This suggests that electrons are being promoted from the valence band to the conduction band, because suddenly by exposing the semiconductor to light, then, and the fact that as a result, I get a conductivity, or the current versus voltage begins to become very noticeable, then I must be getting more up here. And I know from thermal energy alone, I'm only going to get 1 in 10 to the 9. But I can make it more conducting if I shine light on it, because I'm then absorbing electrons into a higher energy level, just as absorbing photons in the hydrogen atom pushes them up into a higher energy level. And therefore, they can get into the conduction band. Okay? So now I can then say, well, what must be happening then is that for wavelengths that are longer than 345 nanometers, the conduction doesn't change. It doesn't help. So I must not be adding enough energy to get the electron to a higher energy level. Okay? But if the wavelength is shorter than 345 nanometers, then there must be more electrons that are making it to the conduction band, and hence it makes sense that the minimum energy required to get electrons in the conduction band is going to be equal to hc over lambda. Okay? Hc over lambda is the energy of the photon. Okay? So the idea is then that I can then calculate what the hc over lambda is for 345 nanometers. It turns out to be 3.6 electron volts, and so I've now found that the energy gap is 3.6 electron volts. By the way, that seems to be a high number for a gap for the semiconductor, but this was done as an example in your book. Why wouldn't this also happen for insulators? Well, for insulators, I'd have to have a lot more energy to get them up into the conduction band. So that's my best explanation I can give you why you wouldn't see this as occurring for insulators. Okay, so now we get to how we do semiconductors and doping. The idea of doping a semiconductor, which actually is kind of like a semiconductor on steroids, so it's actually not too far removed from the sports analogy with doping. But the most common semiconductors in use are silicon. And it turns out that by adding small impurities into these semiconductors, we can increase their conductivity in a very controlled way. So we don't want to turn them into conductors, but we want them to conduct better than what they've been doing on their own. And we tried to do an example of a semiconductor calculation where the gap energy was only 0.55 electron volts. The probability of getting an electron in the conduction band just from the thermal energy, just from the, the 1/2 kT or the 3/2 kT, was only 1 in 10 to 9, right? So the idea with doping is that the goal is to get this higher and to get the conductivity up so that approximately 1 in 10 to the 6th of the electrons makes it from the filled valence band above through the gap energy to the conduction band. So the idea is to get a higher conductivity. So instead of having in our calculation 1 in 10 to the 9 that make it there by thermal energy, we add the impurity and we can get like 1 in 10 to the 6th. Still a small number compared to conductors, but it's a significant dramatic increase relative to the undoped semiconductors. Okay? Okay, so there are two types of semiconductors or doping that we are going to talk about. One of them is called the N-type. Now I guess I can turn the lights back off again. And is it better for the film to leave them on or off?
Yeah, leave them on.
Leave them on?
Yeah.
Okay, all right. Well, I need it off for this one slide.
That's fine.
But remind me, I'll make sure I turn it back on again. when we're done. We can, let's see, is that the way I have it before? I think so. So here's the scenario. The typical semiconductors used in the electronics industry are usually made either from silicon atoms or from germanium. We will study silicon, although the general concepts that you learn would apply to germanium as well. But we're going to look at the ones that are silicon-based, so to make it a concrete example. So the basic idea of silicon, if I take a pure sample of silicon, and you probably have seen pictures of pure silicon from rock samples or sediments in the earth that where silicon is found. They look kind of like a quartz material that are somewhat shiny. The atomic structure of silicon is such that there are four valence electrons. There are 2 in the 2s, and there are well, these don't show the valence, but in G and coli, and does anyone look, does cats have to give the periodic table with the valence in the back? Has anyone seen the periodic table or the valence for the different elements in cats? I know it's in G and coli, so it's, you know, but you can easily find out, or you can, you know, go into Wikipedia too, to find out that for silicon, which is sort of somewhere, silicon Si, where is silicon?
42nd down, or 14th.
Right there, silicon, right? Yeah, Si, right? That for silicon, there are 14 electrons, and it turns out, therefore, 14 electrons, I've got 2 in the 1s, there are 2 in the 2s, that makes 4. And there are 6 in the 2p, that makes 10. So that fills the 1 shell and the 2 shell. That means that with 14, there have to be 4 left over. They fill in the 2s first and then the 2p. So I've got 2 electrons in the 2s and 2 in the 2p. And in silicon, in a lattice structure, the S and P bands are fused or form a continuum. And in addition, there are other electrons that are covalently bonded or shared with each of the silicon atoms so that they can form a filled shell with 8 electrons. And the silicon, the atoms within a solid form a filled valence shell, and the next state up will be the 2s, 3s, 3s, 3p will be the 3D, and that is not filled at all in this model. But the picture that we have of silicon, pure silicon, is the one of the this one as a semiconductor with a complete valence band that's formed by a combination of the 3s and the 3p. And also contributing to that as well are the covalent bonds with additional atoms that form more electrons, as you can see here, to each central one, since the electrons are shared between atoms in covalent bonds. So it forms a filled shell by itself. The next electron can go into the unfilled shell, which then becomes the conduction layer, or the conduction band. So what do we do? So the basic idea of a semiconductor is that at very controlled manner, we replace one of the silicon with a different type of atom, which in this case is arsenic. Now, the reason we choose arsenic is not because it's poisonous and it'll kill people. We choose arsenic because arsenic has an extra electron. It has 5 electrons in its valence shell. So arsenic is AS on this chart. It would be located third, fourth from the right on the periodic table. And this one has 5 electrons in its outer shell, which means that given the bonding with the other silicon atoms, it has 1 electron extra that's not being bonded to other atoms in the silicon environment, right? So this extra electron is more or less free to travel. It is at a higher energy level than the other electrons, and therefore we have now essentially added an electron to the atom, even though you can see the entire sample is neutral, because even though there's an extra electron here, there's also an extra proton in the center of the atom, so it's electrically neutral. But this electron is now free to travel across the sample because it does not have strong bonds as the other silicon atoms do, and therefore it exists at a higher energy level than the others. I think I have a picture of that in just a second. Yeah. So in an atomic energy level picture, what we would say is that the electron in the arsenic contributes an electron that is at a much higher energy level, and furthermore, the conduction band of the silicon is very close to the donor level. So electrons which were added at the donor level can easily be excited up to the conduction band. Now, typically not every single one of them is going to be excited up, but maybe 15, 20, 30% of them will be. So the conductivity is going to increase by adding an arsenic atom, and by controlling the intensity, or I should say the density of the arsenic, we can control the control the conductivity. So typically speaking, about 1 in 10 to the 6th or 1 in 10 to the 7 silicon atoms is replaced by an arsenic atom, and that adds conductivity because of the extra electron. Any questions? No questions? Okay. Good. Now, that's by the way, that is called N-type, because we've added a negative charge carrier to the sample of silicon. We take another sample of silicon, and instead of replacing one of the atoms with arsenic, we are going to replace one of the atoms with gallium. Right? And the difference between gallium and arsenic is that gallium only has 3 valence electrons instead of 5. So there's an unfilled electron site on the gallium atom, which means that there's going to be a very strong affinity from a neighboring atom to allow that electron from a neighboring silicon to jump into that gallium spot. In other words, it's the nature of an almost filled subshell, that if you're only lacking one from that stable environment, that there's a strong electron affinity that can cause or will cause electrons to fill that hole. So that is one particular idea involved here. So now what happens is, if I apply a voltage, then what happens is that the electron moves from a neighboring atom. Let's say I apply an accelerating voltage that will push electrons from right to left. Then this electron here, the neighboring one, fills in this hole, and that leaves a hole on this one. Now remember, these are not static pictures. This is not an electron that's sitting in space, but right, it's orbital motion. But this atom now has 1 less electron in its filled shell, so it can easily grab the electron on the other side and fill that into that hole, and now that hole has moved over to the right. So if I were to keep track of where there was a deficiency of of electrons, which we call the holes. The hole is moving from the is moving from the left to the right, while the electrons are moving from the right to the left, because they fill in due to the directionality of the voltage, right? The applied voltage makes the electric field, and the electric field is going to determine which direction the electrons jump as they move across. But there is going to be a slight abundance of these holes, which are now called the positive charge carriers. So in other words, we look at the absence of electron as the movement of positive charge in the opposite direction that the electron is moving. And we call these carriers p-type because they are, the current is carried by the holes or the spots that are missing electrons. So p-type semiconductors have what we call positive holes that carry the charge, and n-type semiconductors have negative electrons that carry the charge. And the book makes an example of doing an experiment with the Hall probe, which can determine the directionality or the sign of the charge carrying the current in a wire. And experiments done with this have shown that with the Hall probe, that in fact it is the positive, it measures positive charge moving to the right, not negative charge moving to the left. So the whole theory is real. It is not just a conceptual way to look at it, but in fact there is effectively positive charge that is moving opposite to the direction of the electrons. So in terms of the band theory of solids, we have a new energy level, which is similar to the arsenic for the n-type, but except in the p-type, we have created what's called an acceptor level, which is the which allows electrons to jump from a valence band into a slightly higher energy, which is called the acceptor, level, and that distinguishes the two types. So one type is called the n-type, which has the electron, which has the impurity with an extra electron, and the p-type has an impurity with an extra hole, or with a hole, or the absence of electron. So those are the two basic fundamental types of materials that are found in all semiconductors, used in all electronics applications, and they are, for reasons I just described, they're either n-type because they're negative charge carriers, or they're p-type because they are positive charge carriers. Any questions? Okay, we're getting closer. We're getting closer to a diode. Okay, diodes. What's a diode? When an n-type and a p-type semiconductor are joined together, the result is a p-n junction diode. The general feature, and we will describe this in the next slide, so there's going to be a lot more detail, but the general feature is that diodes conduct electricity in one direction, but not the other. So we have what's called forward bias and reverse bias. We're going to study the forward bias first. So notice that we are drawing a picture of p-type semiconductors with these abundance of holes due to the doping of gallium ions, or gallium atoms, replacing silicon atoms. And we're describing the n-type semiconductor with a bunch of minus signs indicating the abundance of extra electrons given by the arsenic. Okay? So we have a geometrical picture of positive and negative charges occurring right here. We're going to look at what happens when we apply a voltage in this mode, which is, we're going to call this forward bias. So the positive side of the terminal is connected to the p-type, the negative terminal of the voltage source is connected to the n-type. Okay. So let's see what happens as take away the battery and just go back to, I have an N-type and a P-type, and I glue them together, I push them together, I bond them together, right? And there's a junction set up between the N-type and the P-type. There's a junction. And what happens at that junction spontaneously, without any voltage, is that electrons from the N-type will spill over to the P-type, and they will fill some of the holes. Right? This continues until there is approximately 0.6 of a volt potential barrier at the junction, with electron excess on the P side and positive hole excess on the N side that prevents further migration. So in other words, if I go back to the earlier slide, and walk twice to open the so when these two semiconductors are joined together, then what I have is, here's the junction. So this up here is the P-type, right? These are the P-type. And this is the N-type. But at the junction, the N-types go and fill in the holes. So at the junction, I'm getting a excess of negative charges here with the absence or the electrons that have jumped away that have left holes behind on this side. So this is creating on the junction a 0.6 volt potential for silicon-based semiconductors. And for germanium, I think it's 0.3, but it's something else. But for silicon-based semiconductors, this is what you have. Okay? 0 point. It sets up, it automatically creates a voltage barrier. Now, let me turn the lights off again. And let's go back slowly. Now I want to turn on the connect the voltage. And maybe I need the lights back on again because it's actually better with the chalkboard than with the slides. So, okay. No, that's not perfect. Yeah, there's lights. Gosh, it's probably going up and down with the light sensor, you know, dimming. Okay, so basically now what happens is that if I connect this, so this is P-type, and this is N-type. And now I connect this to a battery, and this is the battery, like this. So this is the positive terminal, this is the negative terminal, right? Now, the positive terminal is pushing holes towards the center. The negative terminal is pushing electrons towards the center. And you see that there's a barrier here. There's a line of negative charge on this side, a line of positive charge on this side. This is repelling these positive charges. And this is repelling, this line of positive charge here is repelling the negative carriers in the bulk here, right? So there's a repulsion that's set up by 0.6 volts. But if I now apply a voltage that is greater than 0.6, let's say V equal to 0.7 volts, for example, then I can overcome this potential barrier and I will drive the positive charges through right into the barrier region, and the positives and the negatives will meet. I get more positives coming in, more negatives coming up the other way. The negatives jump into the holes on the other side, and I begin to get current flowing across here. In the meantime, as the electrons are leaving across the barrier, I'm supplying more electrons from the battery. So I've got more electrons coming over on this side. Similarly, I'm drawing electrons off of this end, and electrons go over here. So if I were to draw a diagram of the voltage, which is plotted over here, versus the current, then what I would find is that there is, from starting at 0, there is no current at all until I get to 0.6 volts. And then it begins to take off like a rock. So here's 0.6, and here where it becomes really, really huge, it's about 0.7. So the characteristic of this is, I'll try to write this a little bigger, is this is 0.6 and this is 0.7. And the silicon-based semiconductor has enormous, but what happens is that the current is jumping enormously, and it will in fact continue to rise to a very, very high level, which means the resistance is going down. The resistance is going down, and though I get what's called conduction. Right? That's a conductive state. Then, okay, so that's what happens on the positive side. And I think I just described what I was going to in that slide, which is which is what I've already just gone through. Now we want to say what happens to the current. What happens to the current in the diode when the voltage is applied in the reverse direction. In the reverse direction, I have the negative terminal connected to the P side of the PN junction. I have the positive terminal connected to the negative side. And now what happens is that the holes and the electrons are pulled away from the junction. There are no excess electrons to jump across into holes because they've been pulled away, and the current stops. There is no current flow. Because the charge carriers from the N-type and the hole carriers from the P-type have been pulled away from each other. So there's no jumping or filling of the electrons across the junction barrier when you apply this voltage. So that means that going in the opposite direction, that the current is 0 going this way. Right? It's 0 going this way. Right? But then something happens if you start going even further. If you go even further, which in a silicon-based diode is around 12 volts, then there is a strong enough electric field throughout the sample that electrons begin to get ripped off of their atoms and get ripped off of their atoms, and the electrons will flow across this border, this boundary, as if there was no barrier at all. In other words, when you apply a strong enough electric field, the electrons are pulled off of their atoms because there's an external energy source, which is the voltage. They're pulled off their atoms. They begin to accelerate, and then they ionize more electrons and make an avalanche effect. And so those electrons also begin to get pulled off their atoms, which causes them to accelerate, and then they interact with other and then rip off more electrons. As it's an avalanche cascade. It's a cascading avalanche. And the result of this is that when you do this is that what happens is that the current begins to flow dramatically, but the voltage does not change. And this occurs at roughly about minus 12 volts on the bias voltage of the silicon-based semiconductor. So at that voltage right there, or at that voltage, we have what's called breakdown. So breakdown means that the electrons are being ripped off of their atoms, and the current begins to flow regardless of the sign of the voltage. And this is the opposite extreme of the operation of the diode. By the way, there are applications where the diode is operated at this voltage or higher, or there might be, for example, what happens is that you can have a voltage source. If you have a voltage source that operates, we will say from 0 to 30 volts, for example, then this gets clamped at at 12 volts. So no matter how high you try to operate the battery, there is no more than 12 volts that occurs. And this is called this application is called a Zener diode. And a Zener diode is one in which the voltage is is regulated voltage of an unregulated supply is held stable, is stabilized at, Fred, how you supposed to stabilized. You remember how you do it? How it's supposed to stabilized at 12 volts, right? And that's the characteristic of a Zener diode, that you operate it, if you try to drive it harder than 12, it can't go more than 12. So even if you put a 30 volt supply on it, this voltage gets clamped across here at 12 volts. Cannot exceed that. Yeah, so, okay, so that's the theory of what happens in this type of a scenario. And I'll turn off the lights because I'm finished with the discussion with the chalkboard, the whiteboard. And this is the graph that you'll see in your reading material that discusses the operation of the diode. So this is called the IV curve, the voltage versus current that is observed for this type of a material a semiconductor. So we can work an example. Of this. The example that is in your book, we work it out here, is the following. We have a diode whose current voltage characteristics are shown below, and it is connected in series with a 4-volt battery in forward bias and a resistor. And we're asked to find out what resistor is required in order to maintain 15 milliamps of current across the resistor. So this is a simple V equals IR problem, only now we've modified it slightly because our voltage across the diode is held fixed on the positive cycle of the voltage at 0.7 volts. So if we simply take that into consideration, and I know that I have this is the symbol for a diode indicating that current can flow this way, but not the other way, assuming it's not, we're operating in the Zener or breakdown mode. And now what I want to do is I want to make sure that with a 4-volt battery, I have some resistor R that is going to maintain a current of 15 milliamps or 0.015 amps, right? So because the voltage applied is greater than 0.6, I know, or 0.7, I know that the voltage drop across the diode is fixed at 0.7 volts, right? So by the time I get over to this point, right here, I'm down to 3.3 volts, okay? And taking the bottom side, the other side of the battery at ground potential, or 0 volts if you do it this way, then, or if I just use Kirchhoff's law, I get that 4 volts minus 0.7, so 0.7 volts, which is the voltage drop across the diode, minus the IR drop, which is going to be equal to 0.015 times R is equal to 0. So this says that R is equal to 3.3 volts divided by 0.015, which is equal to 220 ohms. Okay. So the resistance I need for this particular circuit to hold it at a current of 15 milliamps is given by about 220 ohms. Okay, well, I think it's a good place to stop. So next time we'll finish up with transistors and amplifiers. And I, by the way, should have homework problems posted for this chapter by sometime tomorrow. But you've got your other homework to work on in the meantime. So we'll finish up then.